In this video, we'll do some more examples of related rates problems. We saw before that we have a problem-solving strategy. We start by drawing a picture and naming the variables and constants. We write down the numerical information that we have. We write an equation that relates the variables together. We differentiate with respect to the independent variable, usually t for time. And then we evaluate. We use known values to find the unknown rate of interest. So here's an example. A spherical balloon is being blown up and the radius of the sphere is changing at a constant rate of 2 inches per minute. Find the rate of change of the volume of the balloon when the radius is 4 inches and also when the radius is 9 inches, so two separate pieces of information, or two separate moments in time. Recall that the volume of a sphere, V, is equal to 4/3 pi r cubed. So that's the volume of a sphere, and we'll use that to solve the problem. So pause, draw a picture, and we'll talk about it together in a moment. Okay, so we've got this balloon being blown up. It's a spherical balloon to make it a little bit easier of a problem, and the radius is changing at a constant rate. So we said that dr dt, the rate at which the radius is changing, is 2 inches per minute. That's dr dt. So this balloon is being blown up, and the question is, what is the rate of change of the volume? So let's see. So we want to find dv dt when the radius is 4 inches and also when the radius is 9 inches. So we want to find it at those two moments in time. Now let's see, we want to write an equation that relates these variables together. We already said that the volume of the sphere is equal to 4/3 pi r cubed. So we'll certainly use that. And now we can basically written down all the numerical information we have already, and we've got an equation that relates the variables together. So now let's differentiate that with respect to t. dv dt is equal to, or the derivative of v is just dv dt, the volume is a function of time. The derivative of 4/3 pi r cubed with respect to t is, so it's multiplied by a constant, 4/3 pi just stays the same, times the derivative of r cubed is 3r squared times the derivative of the inside function times dr dt. So 4/3 pi times 3 times r squared dr dt. That means that dv dt, the rate of change of the volume of this balloon at time t, is 4/3 times 3, the 3's cancel, 4 pi times r squared times dr dt. We were told that dr dt was a constant. We were told that this radius was changing at a constant rate of 2 inches per minute. So dv dt is equal to 4 pi r squared times 2 inches per minute. And so we were asked to find dv dt at two specific points. So dv dt at the time when the radius was equal to 4 inches. So at that moment in time, dv dt is equal to 4 times pi times r squared, 4 squared, times 2 inches per minute, and that 4 is really 4 inches. So we've got dv dt at that particular moment is 4 times 4 squared, 4 times 16 is 64, and that's inches squared, times pi times 2 inches per minute. And so the volume is changing at a rate of 64 times 2, that's 128 times pi inches cubed per minute. That's the rate of change of the volume. When r is equal to 4. And we were also asked when r equals 9. So when r is equal to 9, we're plugging into that same equation, dv dt, the rate of change of the volume when r is equal to 9, is 4 times pi r squared. R is 9 squared times the rate of change of the radius, 2 inches per minute. And so when we, and this is again in inches, so 9 inches squared. And so when we simplify that, we've got 8 pi times 9 squared is 81 times inches times inches squared, that's inches cubed per minute. And if we multiply that out, that is 648 times pi, 648 times pi inches cubed per minute. So this is the rate of change of the volume of the balloon at the point where the radius is equal to 4 inches, or sorry, is equal to 9 inches. Here's another example to try. A ladder that is 10 feet long rests against a vertical wall. If the bottom of the ladder slides away at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Again, draw a picture and pause, and we'll talk about that in a moment. Okay, so we've got some vertical wall, and then there's a ladder resting against it. And so let's see. The bottom of the ladder is sliding away from the wall at a rate of 1 foot per second. Let's call that x, the horizontal distance, and we're saying that dx dt is 1 foot per second. And the thing that we're asking about is the speed at which y is changing. So we're asking what is dy dt, how fast is the height changing? How fast is the top of the ladder sliding down from the wall when at a particular time? So what is this when the bottom of the ladder is 6 feet from the wall, when the horizontal distance x is equal to 6? So that is our question. Do we have any other information? We know that the ladder is 10 feet long. 10 feet, well, that's like the hypotenuse of this triangle. And so we've got this picture drawn, and we've given variables for a lot of these and constants as well. What do we know? We know that dx dt is equal to 1 foot per second, and we want to find dy dt, the change in the height of the ladder, how fast is the ladder sliding down the wall. We want to find that when x, the horizontal distance of the bottom of the ladder from the wall, is equal to 6 feet. So we know what we want to find. We have the information that we know so far. We want to write an equation. So we've done this. Now we want to write an equation that relates the variables together. So again, we've got a Pythagorean theorem here. We've got a right triangle. We know that the hypotenuse squared is equal to x squared plus y squared. The distance to the bottom of the ladder from the wall is x, and the distance, the height of the ladder is y. So we've got this equation that relates to the variables, and both of these x, y are variables in terms of t time. So as time continues, that ladder is moving away, that x and y are both changing. So we're going to differentiate this function with respect to t. Derivative of 10 squared, well, that's derivative of 100, that's just 0, equals derivative of 2x with respect to t, the derivative of x squared with respect to t is 2 times x times dx dt, plus the derivative of y with respect to t is 2 of y squared is 2 times y times dy dt using implicit differentiation. And And now what do we want to solve for? We want to find dy dt. So we're trying to find dy dt at a certain moment, and therefore we're going to solve this equation for dy dt. So we'll divide both, so we'll subtract 2x dx dt to the other side. Negative 2x dx dt equals 2y dy dt. And now we could divide both sides by 2y to get dy dt by itself. Dividing by 2, the 2's will cancel. So negative x over y times dx dt is equal to dy dt. So we wanted to find dy dt when x was equal to 6 feet. So we've got this ladder sliding down a wall. This ladder is 10 feet long, and we're saying when this horizontal distance is x equals 6 feet, what is dy dt? So we see that dy dt is equal to negative x over y times dx dt. We were also given, so this is y, we don't know what y is yet at this point, but we were given the fact that dx dt was 1 foot per second. All right, so now let's figure out what we know. We know x, we know dx dt, we don't yet know y, but we can use the Pythagorean theorem to solve it. So we know that 10 squared plus 6, or 10 squared is equal to 6 squared plus y squared. So 100 is equal to 36 plus y squared. That means 64 is equal to y squared, and so y would be the square root of 64, could be plus or minus 8, but it's going to be in non-negative height, so y is equal to 8 at that moment. And so that means that dy dt is equal to negative x is 6 over y is 8 times dx dt, 1 foot per second. And so the speed at which this ladder is moving down the wall, negative 6/8 of a foot per second. So you could also say that's negative 3/4 feet per second, or negative 0.75 feet per second. Here it makes sense that y would be negative since it is going down, but if we wanted this to be speed, I think speed is always the absolute value of velocity, so speed would be 0.75 feet per second. Okay, here's another example. A hot air balloon is rising straight up from a level field, and it's tracked by a rangefinder 150 miles from the liftoff point. At the moment that the rangefinder's elevation angle is pi over 4 from the ground, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So again, pause, draw a picture, and we'll talk about it together. Okay, so we've got this hot air balloon, and it's rising from the ground, and so it's rising straight up. And we've got something, tracking its angle at different points from the ground. So we're saying, okay, here's this, rangefinder looking at it's 150 miles from the start off point. So it's 150 miles from where the balloon started. And the thing that it is measuring is this angle, we'll call it theta. So we get this piece of information that when theta is equal to pi over 4, the angle is increasing, so d theta dt is increasing at a rate of 0.14 radians per minute. So 0.14 radians per minute. Okay, so how fast is the balloon rising from the ground at that moment? So at this time, what is, and we could call this h or y or whatever, let's call it y, I guess, the height of the balloon. So what is dy dt at that time? So now we need a relationship between these variables, and now we can use trig. So we know that if we have an angle theta, that tangent of theta is equal to the opposite side over the adjacent side. So in this case, tangent of theta is equal to opposite over adjacent. Here, opposite, that's the height of this balloon, divided by the adjacent side length, that's 150 miles. Okay, so now we have a relationship between these variables. Tangent of theta is equal to y over 150. So now we can take the derivative of both sides with respect to t. These are both functions of time. So derivative of tangent of theta with respect to t is derivative of tangent is secant squared theta times d theta dt times the derivative of the inside function is equal to, so y over 150, that's the same as 1 over 150 times y. So 1 over 150 is just a constant, times derivative of y with respect to t is dy dt. So now we want to figure out what is dy dt at that moment. So we're solving for dy dt. We can multiply both sides by 150. So we have 150 times secant squared of d theta dt is equal to dy dt. All right, now we, secant squared theta, sorry about that. 150 times secant squared theta times d theta dt is equal to dy dt. And we are interested in that particular moment of time when theta is equal to pi over 4 and when d theta dt is equal to 0.14. All right. At that time, what are these different values equal to? So d theta dt, no problem. What about secant squared of pi over 4? So that's the same thing as 1 over cosine of pi over 4 squared. That's 1 over cosine of pi over 4 is one of those angles that we know, square root of 2 over 2 squared. So that's 1 over 2 over 4, or 1 over 1/2. And we can invert that fraction, that's equal to 2. So we figured out that this is 150 secant squared of pi over 4. I'll just write that for now. Secant squared of pi over 4 times d theta dt is 0.14 is equal to dy dt. And now we figured out that secant squared of pi over 4 is equal to 2. So it's 150 times 2 times 0.14 is equal to dy dt. And so when we multiply that out, 300 times 0.14, we will get 42. 42 is equal to dy dt. So the speed at which this balloon is rising when the angle is pi over 4 is 42 meters per minute, and that's dy dt.